Buenos días y bienvenidos al webinar.
Good morning and welcome to BrineMine, sustainable extraction of minerals and fresh water from geothermal mines in
Y
Chile.
les
I'm
acompañaré
Denis
durante
Krishna
las
and I will be with you
horas por
the
parte del
next couple of hours on behalf of
proyecto EcoMine,
HK
la
Chile
red
and on behalf of
chileno-alemana que
EcoMine
busca
Concept, a
contribuir a una
Chilean-German
minería
network
más
who
sustentable.
wants to contribute to a more
Nos
sustainable
espera un
mining.
programa muy
We have
interesante
a very interesting agenda focused on efficient extraction and
y
sustainable of lithium and other elements through an innovative approach that will be presented by the
de proyecto
Chilean-German consortium
formado por
BrineMine, such research organizations and industry partners that in a few minutes will be introducing themselves. This is a project supported by the Federal Ministry of Education and Research from Germany, aiming at developing and testing
que permite
technologies that will allow to
térmicas
concentrate geothermal brines to selectively separate minerals and extract fresh water. The goal is to promote the approach,
intercambiar
applications, and to exchange ideas on the various outlooks of valuable mineral extraction from non-conventional sources. As we will see
on
today, there is already a prototype of this technology in Germany, and a relevant goal for the next stage is to finding partners to building a test plant in Chile.
Iris
We
Wunderlich.
have Iris Wunderlich on mining and sustainability of our chamber. Iris, you are in my... Hi, good morning, Denise. Good morning, everyone. Iris will chair the discussion panel, the second part of the webinar on the opportunities and challenges for the non-conventional extraction of minerals. So in closing my introduction, just a couple of technical notes. First, this webinar has a simultaneous interpretation into Spanish and English.
Encuentran un
In
globo
your
donde
Zoom menu, you will find uh, an icon where to select channels of your
directamente
preference. If you are using a web browser, probably you don't have that function. Also, ask your questions using the chat box. We'll try to take them throughout the webinar or directly on the chat box, or we'll be reviewing them so we can publish the answers in the EcoMine concept webpage. Now, let me offer the floor to two of the main coordinators of the consortium, Joachim Kosikowski from the Fraunhofer Institute for Solar Energy Systems, and Thomas Kohl from the Karlsruhe Institute of Technology, and Frank Dinta, it's CSET, Fraunhofer Chile Research. They will be doing the liaison with Chile and the local activities. So, Joachim, please turn your camera on and your mic, and the floor is yours.
Thank you, Denise. I will start my presentation and hope you will be able to see it.
Yes, we can see your screen now.
Is it in presentation mode? No, not yet.
Not yet.
Now it should be. Okay, so a warm welcome also from my side. My name is Joachim Kosikowski. I'm working with the Fraunhofer Institute for Solar Energy Systems in Freiburg, Germany, and I'm the coordinator of the BrineMine project. So a warm good morning to Chile and warm good afternoon to our colleagues from Germany. So in the next couple of minutes, I will give you a brief introduction to Fraunhofer and then show you a bit what we are doing in the BrineMine project. Okay. No, the slide is not changing. So it's just tried it a couple of minutes ago and it was working. I will close again the presentation and do it again. Maybe it's a bit slow. It might be maybe a problem. Okay, well, I hope you see the next slide.
At the moment, we cannot see your presentation, Joachim.
Okay.
Let us know if we should share it. Joachim, maybe we share your presentation?
Yeah. Zoom. Yeah, maybe it's better if you share it.
No problem.
Okay, Zoom view is now gone.
Now we can see your presentation.
Okay. Well, yeah, maybe you can go to the next slide, please. Okay. Well, Fraunhofer is a German research institution founded in 49 after World War II, and it's dedicated to bridge the gap between basic research and industrial application. So we're doing basically applied research, and the entire Fraunhofer society has about 75 different institutes employing about 30,000 employees. The interesting thing is that about 85% of the entire turnover is generated by industry contracts directly or by industrial cooperation and public funds. So this forces us to do real applied research. The society itself has, of course, several projects all over the world, but there are also many different affiliations, which are, for instance, also in Chile. Frank Dinter will later on tell us a bit more about Fraunhofer Chile research. And so there are a lot of corporations worldwide. The problem is that I myself cannot really see the presentation now, but you can go, maybe you can go to the next one and I will do it without seeing the slides. So I'm personally working for Fraunhofer Institute for Solar Energy Systems located in Freiburg, Germany, and we are doing everything somehow related to solar technology. So we're working on photovoltaics, hydrogen technology, and also on solar thermal, of course. And the department I'm working with is called water treatment and separation. And this department focuses mainly on the development of different technologies, for instance, for the liquid-liquid or liquid-solid separation processes. One of our focuses is on the upscaling of treatment processes from lab scale to industrial scale. And we also develop demonstration systems that we operate directly on site at the customer. One of our origins is in the combination of renewable energies with desalination technologies and water treatment technologies, mainly for remote and decentralized applications without infrastructure. So we can go to the next slide. Unfortunately, I don't know what you currently see, but I hope that you see slide 4, which shows the BrineMine project overview.
Yes, we see that one.
Yeah. Okay. So the BrineMine project was initiated in March 2019, and it is supported by the German Ministry of Education and Research under the umbrella of the Client 2 program, which is for bilateral German and external corporations. And the initial operation period was 3 years, but due to the current situation, we will extend this project until 2023. And the interesting thing, so the topic of the BrineMine project is the extraction of valuable materials and drinking water from geothermal resources in Chile. And the interesting thing is that since 2019, there's also a rising interest of this topic visible in Germany. So can go please next slide. I don't, yeah, there are some animations. I don't know what you, yeah, okay. Basically, there is geothermal mining, which is quite new. And on the other side, of course, there's a conventional mining, but there are a lot of synergies. Even though the BrineMine project focused on geothermal use and the utilization of minerals from geothermal brines, there are synergies with respect to raw materials. There are lithium sources in geothermal as well as in conventional lithium mining. Water as a medium is a carrier in geothermal, but as well in many mining processes. And of course, energy is an important aspect. Geothermal is initially meant to produce energy, and the mining sector, conventional mining sector, use a lot of energy. So with regard to the development of the technologies that we are focusing in the BrineMine project, there are exploration technologies, for instance, which are of interest for both sectors. The exploration of the minerals and raw materials is of interest. The extraction processes are of interest, and of course also the energy supply. So therefore, the scope of the BrineMine project is first on the exploration, to develop exploration technologies and to do the assessment of minerals and geothermal resources with respect to the techno-economical feasibility, to develop technologies for the extraction of these minerals, and finally do the demonstration of the technology on site in small scale, but in a real environment. And of course, to encourage the interdisciplinary and transnational research cooperation between Chile and Germany on the academic side, but also with companies. So could you please go to the next slide? So the consortium consists of 7 partners. SEGA is already today represented by its director, Diego Morata. You present SEGA later on. And they are together with KIT. Sakul will present KIT later on, and GTN involved in the exploration and the techno-economic assessment, while our institute from ISE together with the company Solar Spring will develop the extraction technologies, and our partners from Chile, it's from Chile Research, and GTN Latin America will care for the demonstration in Chile. And finally, all partners, of course, are interested in encouraging the interdisciplinary research work. So coming to my last slide, this shows finally the main objectives of the workshop today. The workshop is quite important for us. It's one of the milestones of the project. On the one hand, we want to share our actual research results that we got so far from initial tests in the Upper Rhine Valley in Insheim. We will also get an introduction to this site later on by Mr. Ude. But it's also quite important for us to receive your feedback and your advice from all different levels, and all different stakeholders are on the roundtable later on. I'm also quite happy that Mr. Nunas is with us, and he will give us later on also insights from the ministry, so that we not have only technical aspect, but also the boundary conditions. And finally, last but not least, an important aspect for this workshop is also to find a potential demonstration site. So I said that we want to demonstrate the technology in Chile. And up to now, unfortunately, we don't have a site. So there are companies who are interested to host such a demonstration in Chile. That would be great and would be very helpful for us. So maybe you can go to the last slide, which is only to thank all of you for your attendance. And of course, many thanks to CAMCHAL for organizing this workshop. And I'm really happy that we have so many attendees yet now here. And I hope that we will have a fruitful discussion later on. So sorry for the trouble in the beginning. I don't know what happened, but hope you got my message, and thank you for joining.
Thank you, Joachim. Gracias. Y seguimos directamente con Thomas Koll, del Instituto Tecnológico de Karlsruhe. Thomas?
We don't hear Thomas. You have to unmute yourself.
Oh, sorry.
Buenos
días a todo el mundo. So I'm just very happy that CAMCHAL was organizing this workshop, and we are looking forward for your contributions as well. And but before we start, I think I just would like to also to present you or introduce you a little bit to KIT, the Karlsruhe Institute of Technology, where we have a long-standing collaboration with Chile, especially with Sega already. Go, please, next slide. The Karlsruhe Institute of Technology, it's a major university or a research institution, and that has been founded officially 10 years ago, but it is a result of a very long-standing university. It was one of the oldest universities in polytechnical universities in Germany at all. And it's a merger of this old university and the Helmholtz Research Center. And this got the name of KIT. So in the moment, we have large numbers, something like 366 professors and annual budget of 900 million euros. We have more than 25,000 students coming to us and nearly 10,000 employees. So it's one of the major institutions that covers both research and education in a large bandwidth of applications. So next slide, please. One of these topics, research topics, is geothermal. And we are leading the geothermal energy systems topic in the Helmholtz Association through KIT. And we have a major expertise that is distributed over 5 internal institutes within KIT, covering the aspects from geoscience to material science. And we have 25,000 full-time employees from a running budget, plus 25 further third-party funded scientists. We have 20 PhD students right now, and for example, 2 industry-sponsored chairs. We have a broad collaboration with international partners and projects, and BrineMine is one of them. The Helmholtz, we have a collaboration with our Helmholtz partners at GFZ in Potsdam and at UFZ in Leipzig, and of course with Fraunhofer ESA, which is leading our project here. And further on, we have a broad industrial collaboration with many partners in Germany, in France, and ministries, whatever you want, in the field of geothermal research. Next slide, please. As I mentioned, we have already a long-standing collaboration with Chile. So once when I arrived at KIT some 11 years ago, it was, we started up with the collaborative projects especially in very close collaboration with Sega, with Diego Morata in Santiago at the University of Chile. And so we had two projects, XCAP projects, and we had followed up a multi-GeoX project following up. We are funding the IEDE, the Institute for Eco-Industrial Development. This is a KIT project, not a project of my chair, but a project of the whole of KIT, which is very interesting. It's a virtual German-Chilean Institute for Innovation in Renewable Energies. And we have the BrineMine project that has started in March 2019. And this is, of course, this present project where you can see, I think, these very nice results that will be provided by Valentin and by Daniel. So I would like to stop here. I will come back to you at the end of the course of this presentation and try to make a wrap up of this workshop. Thank you very much.
Thank you, Thomas. Muchas gracias. Y para terminar con este primer bloque, paso la palabra a Frank Dinter de Fraunhofer, Chile.
Yeah, good morning to the Chilean assistants and good afternoon to the Germans. I would like to share my screen with you. I need screen sharing. Okay, everything done. Perfect. Okay, just a few words to Fraunhofer and also to our Fraunhofer Center here in Santiago de Chile. Probably you know that Fraunhofer now is this institute has more than 70 years in Germany, and and they are doing applied research, which is exactly in between the basic research, which is university doing, and the industry. So we are very, very close as Fraunhofer to the industry and developing things as applied technology directly for them. Joachim already said a few things about Fraunhofer in Germany and especially ISE, but we always look that there is sustainability as a basis, and so our development should be social, ecologic, and economic for the clients. This slide was also shown already, so our vision is here in Chile to transfer knowledge from Germany to Chile. And this is exactly what we are doing with this webinar, because this technology was developed in Germany and now it should be used here in Chile. Our mission is really to connect industry here and the technology transfer and rising local competitiveness and innovation. We have two centers here in Santiago de Chile. One is for sustainable biotechnology, and the other one is the Center for Solar Energy Technologies, which is also involved in this nice project, BrineMine. Our co-executors of the Solar Institute here is the University Católica and also Fraunhofer ISE, which is our mother, and we are the little child here. Our goals are to implement the Fraunhofer model and make Chile 100% renewable. And also we are working together with the Ministry of Energy for contributing, making Chile an energy exporter. And our research lines, of course, solar, photovoltaic, and solar thermal applications. Especially, we are working on concentrating solar power and industrial and solar heat for industrial processes. And of course, the water treatment, where BrineMine belongs to. We are also working on new opportunities like hydrogen, electromobility, storage, and economic models. Well, that's it from my side, and thank you very much for being.
Muchas gracias, Frank.
Thank you, Frank. And as you may have realized, we had a little technical issues there with the translation, but it should be working fine now. So with that, we close the introduction and the welcoming words. And now we would like to take a look at the framework conditions for taking advantage of energy and the conditions in geothermal energy from Chile. And for this, we have the participation from Ruben Muñoz, head of the Geothermal and District Energy Unit from the Chilean Ministry of Chile. Ruben, we're very happy to have you with us, and please, you can deliver your presentation. Well, no, thank you so much for having invited me. And I will ask you to please confirm. Can you actually see my presentation? Yes, we can. So as Denise was saying, in my presentation, I will talk about what are the framework conditions for the utilization of materials from geothermal brines, and what is the development of the context of geothermal energy in Chile. So when we talk about this, first it is important to say that we have a Concessions Act, the law number 19,657, which is in force since the year 2000, which basically established that the geothermal resources is a good that belongs to the state, and it can be explored and exploited under concessions that the state can give to the private sector. So the law does make a difference then between surface explorations, which provide the right to undertake all the studies at the surface level, and also deep exploration to determine the geothermal potential existing deep in the earth. It's a concession that can last for 2 years and that can be extended for an additional 2 years. And in fact, there is the possibility to have a future mining concession granted. And it expires 2 years after the exploration concession expires. It can be for a maximum area of 100,000 hectares. And this concession gives the right to take advantage and to mine and exploit the geothermal resource within the limits of the concession. The time is for, it's permanent. It's for an indefinite period, and it can be established for a maximum area of 20,000 hectares. And the law establishes the right to pay for an obligation to pay for a fee, which is about $7.2 per hectare. The law also establishes that the thermal water use destined for health, tourism, or entertainment purposes are excluded. This is the snapshot of the current geothermal concessions in Chile. We have 8 concessions for exploration, and 4 are still requested. So there's only one that has expired that has the right to have the exploitation concession granted later. So when we talk about the geothermal concessions in Chile, this is important. This is an important milestone, and we show this picture every time we can. We have Cerro Pabellón project since 2018. This is a project that was developed under the Apacheta exploitation concession in the north of Chile, in the region of Antofagasta. The concessionaire is Geotérmica del Norte. This is a joint venture between Enel and ENAP. Installed capacity 48 megawatts, invested is $320 million. Now, it is the first geothermal plant at that commercial industrial level in South America, but it is also the world's first largest scale facility at this altitude to 4,500 meters above sea level. This slide also shows the geothermal potential of high enthalpy. This is work that was done jointly with the industry in Chile within the framework of the Geothermal Commission that was put together. This is not the potential of Chile, but it is rather the potential of the areas that have been explored. And that's why the participation of all of the companies was so important. They shared the data that they concluded for each of the areas with us. For example, the project de Cerro Pabellón is here. This is Apacheta, and this is the north of Chile. And here, this new continuous map, this is the central southern area. And currently we have two operators aside from Cerro Pabellón. We have the Energy Development Corporation, which has the project called Mariposa here in the region of Maule, and also Transvac that has the project with the concession called Peumayen here in Arauco here. These two are looking at how they can start the drilling this year. So you can see that the geothermal potentials are on the mountain range, away from the cities and consumption centers, but they do have areas with that they share with the indigenous communities. On this slide, I just want to show the objectives regarding the policies that the government has committed to within this energy route between 2018 and 2022. This is the energy agenda. And with regards to geothermal, well, I'm not going to go in depth here, but just the first one, which is modifying the Geothermal Act in order to try and facilitate the development of geothermal processes that are smaller, that do not require a concession. There will be a special permit granted to them. Another important development that is mentioned here is that currently we're implementing the flexibility of the electricity system, trying to allow a larger amount of renewable energies being included into the system. But we know that this creates a challenge in order to manage that system so that it can be a safe operation. So for this, we're putting together this flexibility strategy with the aim of trying to acknowledge and also trying to favor the development of stable, sustainable, renewable energies like geothermal or other sources too. Another important milestone is the decarbonization commitments. You know that Chile has come to the goal of having carbon neutrality by 2050. And one of the important ones, or one of the important commitments is to close all of the coal-fired power plants by 2040. So this exit of the coal-fired power plants is also an important opportunity for geothermal projects because the coal or power plants and the geothermal power plants are very similar in a sense. They work 24/7, they have high plant factors. So that is the most important information regarding that slide. Onto this slide, which are the framework conditions then for the extraction of minerals from geothermal brines? And here we have this slide then where we can show the kind of concessions that the law has. This is already part of our legal framework. Article 28 establishes that mining concessions and other rights can be constituted on geothermal concessions because the mining resource is also recognized as a good that belongs to the state, so it can be explored and exploited. So mining concessions and other rights can be constituted on geothermal concessions or others, for example, tourism or water concessions. Article 28 also says that if the owner or the holder of the owner of the concession causes damage to another, there has to be a compensation. Article 29 it says that if in the same area there is a geothermal concession and a mining concession belonging to different holders, Article 20 says that if as a result of the exploitation of the geothermal concession, there is a mining potential, then the owner of the geothermal concession must inform this to the mining concession. And then they can request that this mineral be delivered to them, but they must pay the cost that the geothermal concessionaire has had to incur into in order to deliver these mining products. Finally, the law says that if the mining concessionaire rejects receiving these minerals, then the geothermal concessionaire can use those as they best deem. This is in the case that we have two different holders in one same area. Also, we could have the case that if there is one that has the geothermal and mining concession, it's also covered by this law. And this is my last slide. These are not specific provisions that are part of the law, but they are part of the regulatory framework. The first one is we need to remember that when we talk about geothermal energy, we're talking about a renewable energy source. Therefore, the operating conditions must be so that they must allow for the sustainability of the exploitation of these resources so that we can have this as renewable energy. So that is considered also for the recovery of minerals coming from brines, so that because that condition cannot affect the fact that it's a renewable energy. It must not allow for this resource to be at risk. So basically, this project that tries to see what are the technical and economic possibilities, there's also a good possibility here for to try and see how this extraction can be sustainable in time to make sure that the geothermal resource can be sustained in time and not impacted by the extraction of mineral. Also, the law establishes of having the water rights granted by the law, but it also says that these waters cannot be used for the means of the geothermal concession. That is to say, that the waters cannot be taken advantage for other purposes, for mining extraction or others, for example. And that's something that needs to be looked in more detail when it comes to our regulation. Another important point, I talked about the indigenous communities in the geothermal areas. This is a relationship that has not been easy between the geothermal community and the indigenous communities. So the ministry has tried to communicate, to disseminate what geothermal energy is and how it can be developed without affecting the indigenous communities. And SEGA has been with us in trying to establish this base and trying to communicate this. One of the problems is that the indigenous communities do not want their water supply to be affected. So this is one of the things that we've had to constantly communicate. And I'm saying this because under this scenario, a project that wants to extract minerals or fresh water must be concerned with communicated that the conditions for the local communities must not be impacted. Well, and lastly, obviously, the environmental regulations. This is important because all geothermal projects, especially a power plant larger than 3 megawatts, has got to go through an environmental impact assessment. So all environmental impacts must be considered, and we have to see what is the effect or the environmental impact that could be produced when extracting minerals from geothermal fluids. That's basically what I wanted to share with you. And I want to congratulate you for this initiative. And I hope that it will be very successful. For us, it is very important that we can truly add value in terms of these renewable energy sources. And we wish you the best of success.
Thank you, Ruben, for your interesting presentation and this overview on the boundary conditions, which is an input for our discussion panel, the second half of the webinar. So thank you once again. We'll be sharing all the presentations after the webinar in our web page of EcoMine and Concepts, and we received several questions. We're selecting them to answer them during the webinar or having them posted on the web page. Now, into another partner, the Center of Excellence of Geothermal of the Andes, SEGA, Diego Morata, Director. He will be explaining the potential of geothermal energy use in Chile. So, Diego, the floor is yours. Thank you, Denise. Let me try sharing my screen, or maybe you can do that for me. Well, we have your presentation, Diego. We can do it for you. Yes. Right now, if I share my screen now, okay, it's easier if I do it from my end. I assume you can see my presentation right now. Let me go into the presentation mode. Good morning, everyone. Yes, I'm Diego Morata. I'm director of the Center of Excellence of in Geothermics in Los Andes. Having discussing with you from the academia, what's the overlook of geothermics? We are a Fondart project funded by NIT, what used to be CONES. It's the main organization of the University of Chile in the Department of Geology, and Catholic University is an associate organization. Why geothermal? That's the first question you should ask. And Thomas said we have spent several years with high tech. But why geothermal? Geothermics is the only renewable energy that can be produced and generate electricity 24/7. It's a great versatility. In this webinar, we see how geothermal energy, besides electricity, besides power, may be used to recover lithium or even producing water, drinking water, or industrial water at the very least. And very important thing, has very little impact. Geothermal plants have a small footprint and very low emissions of greenhouse effect gases. We all know that the development of a geothermal project has a high risk factor upfront, lots of uncertainty at the minor risk. But once the resources are recognized, the risk is fairly low, and these may be developed quite flawlessly. Why geothermics in Chile? This is a question somebody already asked. Chile, it's in the unique geological context where we know we have the subduction of Nazca plate under the South American plate and the subduction of the Antarctic plate. And we have a volcanic chain going from north to south with a huge volcanic activity that is shared by other countries in the of the Andes. But Chile is quite relevant because in the Andes, the this country has the highest concentration of active volcanoes. As we can see in different scales, this is an interesting paper published a couple of years ago where uh, this is a calculation of the geothermal potential for South America, analyzing the temperature of the ground. And let me focus here how the geothermal gradient, how the temperature increases as you go deeper. This is the area, both northern, central, and southern Chile has the highest thermal gradient. That is, we have a huge potential throughout our country. In fact, with the SEGA, we have identified several areas using different methodologies that may be used as highly favorable areas in yellow. Areas of interest with the green, we still one third of the country in the southern country that also has areas of interest, but because of the image, can show everything in one single slide. But we can see there are areas of interest all along the country, areas with highly favorable areas, areas where you have inferred resources, and as Ruben said, that was the source for obtaining the data, worked in the geothermics task force, indicated resources where we saw the reservoirs, and one single power plant at Cerro Pabellon. So we should wonder why, with so many geothermal resources, why only one plant is in operation. And we can see that the history of exploration in Chile began but in the early 20th century. The Italian Society of Antofagasta hired the engineer Tocchi to analyze the geothermal resources in northern Chile. Back then, in 1910 and 1913, the idea was that at El Tatio, we could install up to 50 megawatts. To put this into context, back then, 1915, 1920, in Italy, they only had megawatts in their grid. So the potential of northern Chile was much higher than the whole potential of Italy. So in Chile, there were several phenomena, especially associated to uh, uh, shutdown of the pipeline with Argentina, uh, dry years, a huge drought, which made the geothermal industry to be regulated. The new law favored the development of geothermal energy, but in 2014, several exploration concessions were applied for. Some numbers: in 2014, there were 75 exploration concessions and 8 for exploitation. And some were in the process of being approved, 56 and 20. Ruben, just to show the recent numbers. Today we have 0 exploration concessions and 4 of exploitation. So this gold fever, or geothermal gold fever, is gone, and today is a sad reality is that there are little geothermal explorations in the country. In fact, there is only 3 projects that are underway: Cerro Pabellón, Mariposa, and Peumayén, which used to be known as Tolhuaca. Cerro Pabellón, as Ruben said, is in northern Chile. In a This is El Tatio. It is geological sector with a high geological interest, is where Cerro Pabellón is located, and some geological features. I will not elaborate on this, but Let me say that thanks to a collaboration program with ELEN and Power and Geotérmica del Norte, we at SEGA, we are conducting research to understand the geothermal resources at Cerro Pabellón. It is an incredible area, difficult to work. It's 4,500 meters above sea level, 48 megawatts and with an expansion plan to up to 33 megawatts. So by late this year, we will have 81 electric megawatts. Uh, with the 48 megawatts, you can supply, you can meet the needs of Calama, for instance. If we go to central Chile, we have Mariposa. It's a EDC, that's a Philippine company which has the concession. Talca is 250 kilometers south of Santiago. And then we have the Mariposa project up in the Andes, where the geothermal potential could be in the order of 100 megawatts, maybe more, where some wells were drilled, but right now this whole project is in standby. I mean, because of the market conditions. And the third, the geothermal field, is Peumayenne, even further south. This is in the border between Biobío and Araucanía region. The Developable Energy, then Right Red Power, and Transmark are now developing these projects. Let me say that they drill the Tol Cuatro production well with a potential of 12 or 14 megawatts. Today it's an interesting project with a proven resources. Again, is standby given the economic conditions of the electric market. Chile's potential, it's huge, but it is unknown because of the lack of data. We did run some analysis with the geothermal resources which are better known as published in this paper. In fact, this was the basis, the foundations for this work that Ruben referred to on the geothermal task force. The, with those areas with the better knowledge in terms of exploration by companies, this one here, we reached the conclusion that by 2030, there could be 1,500 megawatts, and by about 600 megawatts, and 2050, 1,500 additional megawatts if the economic conditions are right. By 2050, we could have 2,000 megawatts of electricity using geothermal energy. As Ruben said, it's not our potential. The academic numbers show that the potential could be around 40,000 megawatts. These are numbers based on academic analysis. And if you want to be more conservative, this would be the actual numbers based on on data supplied by the industry. And these 2,000 megawatts, they may reach 4,000. Well, today, as we have seen, we have only 48 megawatts installed at Cerro Pabellón, thanks to green power, 33 additional megawatts, but that's it, that's all. So we have a problem as a country because the amount of coal in the plants running at coal, which have to be decommissioned by 2050, it's about 5,000 megawatts worth of coal, and the only advantage it has is that could be used as base energy because they can work run in 24 hours a day. The only renewable energy that can supply this energy is geothermics. So, as Ruben Munoz said, uh, Chile's bet on a coal-free power mix should be the big encouraging factor for geothermics. And there is a new player called green hydrogen in the last few months. The government has built a plan called the National Strategy on Green Hydrogen, where we proposed green hydrogen production using renewables. But they also refer to wind and solar. Geothermal is not in this document, and this is a political decision which is hard to understand. But this BrineMine project, it's the opportunity to prove that geothermal energy, it's part of this concept of circular economy. Not only power, not only electricity in different areas of the country, but we can extract or recover strategic metals. Valentin will elaborate on that. And also, we could have hydrogen production plants throughout the country because geothermal resources are all over the country. So, in conclusion, I would say it's a terrible situation here in Chile, even though we have a huge, high enthalpy resources in the Andes. It's difficult for them to be developed given market restrictions and free market, which is that prevails in our country, despite having more than 2 gigawatts available by 2050. We need a clear transition. Over 5,000 coal-based megawatts that have to be removed from our power mix. And this should be a great opportunity for geothermal power. It would be a government decision betting on clean, efficient, proven technologies. So the actual interest should be a mandatory part of the constitution that will be drafted in this country. This is the opportunity once and for all to go for clean, renewable energies, of which Chile has ample. And there is an opportunity for medium enthalpy systems, smaller plants, or even direct use of geothermal power. This is unknown here in Chile. This is a field, it's an amazing field of opportunity. And green hydrogen, of course, that's a new opportunity once again. New Zealand is already thinking of producing green hydrogen with using geothermal power. Germany, if you have this power source, why not using these to generate green hydrogen using geothermal power and adding value to these geothermal resources? There are tons of lithium, which are extracted, which are recovered, and then are reinjected. Rare earth, gold, which are being extracted, going through the plant, and then being reinjected. This is an opportunity for the future, an opportunity for a much more sustainable world. Thank you very much.
Muchas gracias, Diego, por darnos este panorama de la situación
Well,
actual y los
thank
proyectos
you,
que
Diego,
ya
for giving
existen
us
y los
this view of the projects that are already existing. And we know that this is an opportunity then that exists for geothermal energy in Chile and for the BrineMine project. So thank you so much. And again, now we want to know the results of the BrineMine project and the economic considerations. And after this presentation, then we will have a short round of questions and answers. We're tight with time, but we will try to answer some of the questions that we will get. So with this now, I give the floor to Daniel Winter from Fraunhofer and Valentin Goldberg from the KIT.
Okay, thank you, Denise. So I will start to share my screen. Okay, so it works. You can see the right screen?
Yes.
Okay, perfect. Then it's now our pleasure to present you our scientific results and also the economic considerations about the BrineMine project. Since we've heard now a lot about the geothermal potential, we want now to outline the potential of a combined raw material and freshwater extraction from geothermal brines in Chile. We can roughly divide our BrineMine project into three major parts. One part is the exploration. A second part is the development of extraction strategies. And the third part is the prototype development and operation. So let's start with the exploration. As we've seen in the presentations before, we know that Chile has one of the highest geothermal potentials worldwide. Also, we know from fluid chemistry that due to the high temperatures of the geothermal reservoirs, these waters can have large amounts of different elements which they dissolve in the depth in the reservoir. Our research has shown that 12 out of 30 worldwide critical elements can therefore be enriched in these geothermal brines. But also, we know from our literature studies that the data sets are lacking of data. We have mainly just the results of the main element analysis, but trace elements, for example, as lithium or rubidium, are lacking in these data sets. So therefore, one perspective of our BrineMine project is to make a large-scale geochemical sampling campaign in the north of Chile to see what elements are in fact in these brines enriched. But we do not just want to talk qualitatively about the elements which are in these brines. We also want to quantify our fluid pathways. Therefore, we combine our geochemical exploration with geophysical exploration. One technique we use there is the international approved approach of magnetotellurics. There we use the technology that the saline waters in depth have a higher conductivity than the surrounding subsurface. Therefore, we can make the fluid bodies in the subsurface visible. So we cannot just say where our water is coming from, but we can also see, as for example here, how large the water bodies are in fact in the subsurface, as we did here in Toluaca. So that means that we cannot just qualitatively describe where our raw materials are occurring and what raw materials are occurring, but we can also see how large our geothermal reservoir is, and with that, how large our potential for raw material extraction is in these reservoirs. But let's talk about if there is a potential, an economic potential in raw materials from geothermal brines. Therefore, we started some first economical considerations. Since we unfortunately could not conduct our geochemical sampling campaign, we started our research with existing data. Therefore, we use data from different springs all around Chile, and we take a closer look to different elements. We focus not just on one element as lithium, but also trace elements as rubidium or cesium, or also more enriched elements as boron or magnesium. To elaborate the economic potential, we developed a simplified production scenarios. The high economic potential does not come from the large occurrence of these elements, because we can see that just some milligrams of them, but from the high circulation rates we have in a geothermal power plant. So we start with a typical flow rate of 80 liters per second. Under an availability of 90% time of the year, this results in a really large amount of circulated brine per year. Further, we assumed an extraction rate of raw materials of about 50%. This is just a basic estimation to make a quantification of the potential. For example, the research of lithium predicts an extraction rate of 80 to 90% using iron sieves for extracting lithium from geothermal brines. So as a result of our initial content of the raw materials in the brines, in combination with our annually circulated brine, as well as with our extraction rate, this results in the circulated mass per year. We can see here. There we can see that we have, according to the total amount of our elements, we have different enrichment in our circulated brines. Also, we looked up in different commodity tables the prices for different elements. There we choose between pure elements, as for example for magnesium or cesium, or also different compounds, depending on the different commodity markets. As a combination of the specific price and the circulated mass, we then result our economic potential. And as we can see here, different elements have a high economic interesting potential. For example, with our lithium, which has a quite interesting potential, but we also have like hidden champions as magnesium or boric acid, which are having similar economic values. Further, we have really highly interesting elements as cesium or rubidium, which are in fact one of our least enriched elements in the brines. So we can say after a first study that we can not just derive elements for battery or high-tech technology in our brines, but also from different kinds of industry. In our first approach in extracting raw materials from thermal brines, we yet focused on the element with the lowest economic potential, on silicon. But why did we focus on silicon in the first place? This is because of silicon's special geochemical properties in geothermal waters. We know that the solubility of silicon is increasing with increasing temperature. So here we can see the possible solubility of SiO2 in comparison to the temperature. We know, since silica is one of the most abundant elements in the Earth crust, that our brines are saturated with silicon with respect to quartz. If we now produce our geothermal brine from a reservoir, for example, with 200 degrees C, into a surface power plant, we cool down our brine. This is then we're going to the part on the left and cool our brine. So if we then reach this red line, we are overreaching the maximum saturation of our most solutable silicon compound of amorphous silica. So if we hit this saturation line, this means that our brine is oversaturated with respect to silicon. And this we know for a long time in the geothermal industry is then known as silica scaling. But this is not just a problem if we cool our geothermal brines for geothermal energy production, but also for water treatment in waters with high silicon content. So therefore we can say that silica is a limiting factor for geothermal energy production and associated raw material production. So therefore we had at first to find a way to reduce our silicon effectively and selectively, because we do not just want to reduce the silica, we also want that it does not affect any potential other target elements. So therefore we started our laboratory studies using artificial brine, which we designed after the role models of the brine of El Tatio, that we have some Chilean basic result for us. A fundamental approach is that silica has different charged species in its aqueous form. So in a neutral water, silica has no charge at all. But if we increase our pH value at the brine with an addition of, for example, sodium hydroxide, we bring our silicon phase into one times negatively charged phase. If we then add a positively charged cation, for example, calcium, this results in a strong reaction and formation of calcium silicate hydrates. And this is the fundamental approach, that we bring our silica into a negatively charged form, add some positively charged ions, and then bring it to a precipitation. This we evaluated with different reaction agents and tried our best to find the perfect sweet spot to make a most effective reduction of our silicon in the brine. And with this approach, we were able to reduce about 95% of silica from our geothermal brine, which resulted in a precipitation of this bright silicon compounds. And with this small scale experiments, we continued and brought it to a larger scale at the Fraunhofer Technical Center in Freiburg.
So hello, I hope you can all hear me.
Yes, perfect.
Okay, thank you, Valentin. So I will hand over this presentation at this point, and I want to go into the strategy of turning this idea of silica reduction into an industrial process in the framework of geothermal waters. So we can see a typical geothermal power plant. We have the geothermal brine source, and we extract heat at a high enthalpy level for electric power generation before reinjection into the well. So at this point, we want to attach our brine extraction, and we take part of the brine out and process our first water treatment step, which is the desilicafication. which is done by reactive precipitation, done with calcium precipitation, as Valentin has just shown. Then this step is followed by a pre-concentration step driven by pressure-driven reverse osmosis in order to produce fresh water and rise the concentration of the still dissolved valuable compounds. And since the pressure-driven reverse osmosis is relying on electrical energy, we directly use the generated power on site. Then this process is followed by a post-concentration step, which is shifted to a thermally driven process called membrane distillation in order to further push the concentration to higher limits and extract water. This thermally driven process exceeds the borders in terms of high salinities in comparison to the pressure-driven processes. And this process can rely on low-grade waste heat, so we can also drive this process from the thermal energy supply on site. Then this process is followed by selective extraction processes of different target elements, of rubidium or cesium. In the BrineMine project, as Valentin already introduced, we focused on the desilification and the concentration step in order to prepare the brines for any target extraction, since the selective processes for extraction always are higher in performance with higher concentrations. So we turned this idea into an engineered hydraulic design. I don't want to go into depth into this rather more complex hydraulic schematics, just give you an idea what we have realized in the framework of BrineMine. We have the first process from the geothermal brine inlet and the silica reduction in steered reactor tanks, which is followed by the precipitate extraction, which is a filtration step. Valentin, can you please click? Which is then followed by a first concentration step, the pre-concentration with reverse osmosis, and then followed by the post-concentration step, the thermally driven membrane distillation. Next slide, please. So as a first showcase, we selected the Upper Rhine Graben showcase because it is there is a very interesting brine composition, and there is a running geothermal power plant project in Insheim. So we had access to these brines. I want to share some of the water chemical analysis of these brines. We can see that in the table on the left-hand side. We see this is a very high salinity brine exceeding 100,000 ppm of total dissolved solids. Additionally, we have a quite interesting amount of dissolved lithium, which is about 165 ppm, coming along with a high level of calcium, which can directly be used for the precipitation of the lithium, for the precipitation of the silicon, sorry. We can see a rough schematic of the power plant. You will hear a lot more detailed information on this project from my following up speaker, Mr. Ude. But just roughly, we have the extraction from the brine from the reservoir with the extraction pump, followed by a particle filtration, and then the heat extraction. The brine is cooled down from about 160 degrees to about 60 to 70 degrees, depending on the season, for the electric power generation based on an organic Rankine cycle. Before then, the brine is re-injected into the reservoir. And the point after the heat extraction is the access point of our demonstration plant. So in fact, we built two generations of demonstrator. The first we could call a demonstrator prototype because it was meant to be a flexible semi-automated test rig to go on site and see how the water chemistry behaves and how our components and automation strategies work. You can see here the modular two-stage precipitation reaction system with flow controlling, dosing control, and the MD post concentration on the test rig. And this experience from the initial field test then ended up in the design of a final demonstrator, which we also commissioned in the field. Here you can see on the picture the installation on site, and I will guide you a bit through the main components. First, you can see the switch cabinet controls and data acquisition. Then you can see the reactor, which is designed as a continuously steered tank reactor and transparent so that we can see what's going on with the brine. You can see the dosing station for different dosing agents, which is done so that we can treat very different kinds of brines, for example, composition as in the upper Rhine Graben, but also totally different brines as, for example, the El Tatio brines we have studied in the lab before. You can see the continuous band filter, which is used to then extract the precipitates out of the brine. And then the pressure vessel for the reverse osmosis membrane system and the neutralization tank. At last process, you can see the post-concentration MD stack, which is provided in an external system from the project partner Solar Spring. This system was then transported to the power plant in Insheim and commissioned and operated early this year in February, March. So here you can see some impressions from the operation. On the left-hand side, you can see the whitish brine in the reactor. After the inlet, we can see the dosing reactants. We can see the precipitates settling in gravimetrically and snowing to the ground of the transparent lamella settler. And you can see the filter cake of the band filter continuously carrying out the precipitates out of the filtration system. And at this point, I will hand over the presentation back to Valentin that will give you some more insights in the scientific results of this field test operation.
So, thank you, Daniel. So after we have seen now the image and the implication of our procedure in the field, I want to now give you an overview of what is happening behind there in the chemistry. So most importantly is our silicon content. So in the following graphs, you will always see here the content of the different ions, and you will always see this area between the red bars. This is the background of the natural variation of the waters in the geothermal power plant. Since we were operating in a real life environment, in a real operating power plant, in a continuous flow, we had some natural occurring variation in our waters. Therefore, during all our procedure, we made background measurements of the untreated waters that we can see what is really an effect of our treatment and what is just a natural background noise. Also, you can always see the comparison of the untreated water and the treated water for one of our experiments. Most importantly, we could say that we could reproduce our silicon precipitation in a real-life geothermal operating power plant. And we could not just reduce the silicon effectively, but also really fast. The whole silicon precipitation takes place in less than 5 minutes. This will be interesting for a later large-scale prototype because the faster our reaction kinetics are, the better it is for the real-life field implementation. Further, we can also see that our calcium is greatly reduced. This is because of our calcium is the reaction partner of our silicon. Further, as a reference for a future extraction target, we can see that our lithium content is not reduced. It is just ranging in the variation of the natural background. So we did several experiments and we had also some results where we have in the second stage, in the treated water, we have more lithium than our first reactor, but this is just an effect of the background noise. But we can say that our lithium is not reduced in any of our processes. And lastly, we can also see, of course, that our sodium is increased, since our sodium hydroxide is our reaction agent to bring our pH value to 10.5, where the precipitation is initiated. But let's come to the point why we all did this. We want to post-concentrate our brine and extract fresh water from it. And this we did in the first experiment, and also quite successful. You can see here the results of our concentration experiment. The dots are representing different elements you can see here, which were concentrated up to a factor of almost 3, leading to a total salt load in our brine of about 300 grams per liter. Also, we could with this increase our lithium content up to about 500 milligrams per liter. And which is also mostly important, that our silicon content does not increase significantly. And why this is important, I can show you now. Because this is the point where we started with our silicon. So this is the initial silica in the geothermal power plant in Insheim. And this is how the silica would develop if it would be untreated. So, but now we have to look closer at the saturation of the silica. Therefore, we made a numerical iterative simulation, which shows us the maximum possible solubility of silica in the treated brine. You can see here that the possible solubility of silicon is reduced by an increase of our total dissolved salt load. But we also can see that our red line, the calculated maximum solubility of silicon, is intersecting our initial silicon value. So this means that our brine is already saturated with respect to silica when we start our precipitation process or our concentration process. This means with every enrichment step, we are oversaturating our silicon in our brine more and more. This would lead to a really great scaling potential if it was not be treated, because we can see here, if it would not have reduced our silicon in the first place, it would be now at a concentration of about 250 milligram, while we only can dissolve about 60 milligram per liter. But since we reduced our silicon from our brine, we could even increase our silicon content even more, since we're still far away from our saturation. And this shows that our experiments could not just be successfully implemented in a real scale environment, we also can show that it was necessary, because otherwise we would have a damage on our extraction facility and would have a silica membrane fouling. So concluding, we can say that there's an enormous potential of raw materials stored and circulated in geothermal waters, circulated in geothermal power plants. And our extraction and our exploration campaigns will bring even more to light. Also, we could say that we could successfully develop a precipitation, a selective precipitation method from scratch in the lab, and bring this into a pilot plant scale in a real-life operating geothermal power plant. The next step is now to bring all this to its original place, to Chile, and bring it to you. And before we will leave you with this presentation, we also prepared some more visualized impressions from our prototype testing phase we had in Insheim.
Can you hear me?
Yes.
Okay, I will give some comments. Here you can see the prototype on site in Insheim, the power plant. Here, this is our access point. And if we turn the valve on, then we start with the filling of the transparent reaction tank. Here we see the brine is entering and slowly filling the tank. You can see the screens of the control systems. And we can see that the brine is quite warm. Steering is started, and here we can see the initial adding of the reaction agent directly starting in the formation of the silica precipitates in the form of white flakes. And if we reach eventually steady state, we see a whitish slurry, which is brine. In steady state, we started to sample for chemical analysis to end up in results, as you have just heard from Valentin. The next step is the separation of the solids from the fluid. You can see the band filter working and continuously extracting the precipitates, so that we end up in a precipitate mud and some clear phase for further treatment. Here we can see the unfiltered and the filtered brine. The clear phase is then pushed forward into a neutralization tank, stabilized and prepared for post-treatment. We were collecting this water in big IBC tanks in order to do studies for the extraction processes and the downstream processes.
Okay, and with this, we are also at the end of our presentation about the results and the economical considerations. We thank you for your attention, and we would be happy if you would get in contact with us.
Gracias, Valentin y Daniel. Nos gusta...
Thank you, Valentin and Daniel. We would like to answer two questions from our audience. Unfortunately, we don't have the time to take more questions, but as I said, we'll be reviewing the questions after the webinar, and we'll try to post the answers in the webpage. And for the questions, we have Iris. You have a question for Valentin and Daniel? Yes, we have two questions for Valentin and Daniel. And the first question is from Humberto. I will be asking this in English because this was written in English, Valentin.
Feed pressure used in the RO unit. The osmotic pressure could be high in this high saline brine. Could you refer yourself to the pressure, the feed pressure in the unit?
So I guess I'm answering this question. The issue, you are totally right, due to the deal with this heavy salt-loaded brine, the RO pre-concentration step is bypassed in the demonstration site in Insheim because it is already exceeding the typical pressure levels required for such treatment. So here we directly refer to the thermal post-treatment, but we are already at a very high initial trace element concentration range. So the demonstrator, since the demonstrator is originally built based on a composition of a El Tatio brine in Chile, and this one has a significantly lower salt load, we decided to have a energy efficient pre-treatment step, a pre-concentration step with RO to actually reach levels that are already existent in Insheim. So in Insheim, we needed to bypass that step because it doesn't make sense at this brine and directly went to the thermal process. But we're hoping that since the RO is installed, that we can operate this in a brine that works, that has lower salinity levels in Chile. And the pressure level that is the demonstrator is capable on operating is 70 bars.
Muchas gracias. Y otra pregunta para Valentin y Daniel.
Thank you. Another question for Valentin and Daniel, again in English.
To analyze or to evaluate the porosity and or pore connectivity of the brine post-rock, and also to measure the brine electrical conductivity by itself.
So in the first place, we start our approach for elaborating different reservoirs on the geochemical base by analyzing the subsurface, the surface outflows. And the second step are our geomagnetical measurements using magnetotellurics. And with this, we are measuring the potential conductivity differences to highlight or to make the fluid bodies in the subsurface visible. Just the question again. The electrical conductivity, we of course measure in the brine in the first step when we sample our waters, because this is a good indicator for the initial salt out of the brine. The pore interconnectivity, which was also mentioned, is not yet a subject for our exploration campaign, but will come if we look to the different reservoirs in more detail.
Maybe I also have some addition to this question. On the demonstrator itself, we refer to the inline electrical conductivity measurements on different places in the process line in order to track and control the different concentration step and in order to adjust the concentration intensity of the individual step according to the requirements of a specific brine.
Muchas gracias.
Gracias, Valentin. Gracias, Daniel. Y gracias también,
Thank
Iris.
you, Valentin. Thank you, Daniel. Iris, one last question, very quick question. Is there any web page where we can have or get more information on the technical process of BrineMine? Do you have a web page or a website where we can find this information?
I can forward, of course, the project page of BrineMine, and there you can also see some videos and also publications out of the BrineMine project. I hope this will help, and also we are always there for answering your question. You can contact us under the given email addresses.
Super, gracias, Valentin. Entonces, seguimos con la siguiente presentación.
Thank you, Valentine. Next presentation, and we will now virtually go to Germany in time. Well, we have Jörg Ude on his outlook on the energy use and material extraction from geothermal brines in the upper Rhine Graben. So, Ude, the floor is yours.
Thank you very much, Denise. A warm welcome to our Chilean and European attendances. I believe you will see my presentation now in the presentation mode. So I will give you a short overview about the potential for the energetical material utilization of geothermal brines with the example of the Insheim geothermal power plant in Insheim. So just to give you a short overview about the geothermal play in the upper Rhine Graben, which is directly in the cross-border section between France and Germany. So it's in southwestern Germany. It's a very promising resource. As you can see here from this presentation, we have 5 geothermal sites already in operation, 3 of them in Germany, 2 of them in France so far. But a lot of them are potentially new projects in the upcoming future up to into the next 5 or 6 years. So we believe we expect 3 to 4 in France in the next future, but the more of them on the German side, especially more on the eastern side of the Rhine Graben. Both of them will be private finance projects, but also projects organized and financed by several public utilities or communities. So the Rhine Graben looks quite promising and will develop up to the more dominant geothermal play together with the Bavarian Molasse Basin close to Munich in the near future. But coming back to the Insheim project, a short overview about the project development story. So the project has been started under the organization of a private project development company, the Hot Rock Engineering Company from Karlsruhe. So it's situated at the same place where the KIT is situated. And after some substantial exploration processes, they started the first drilling operation in November 2000 or in June 2008. So the first well was successfully drilled at the end of 2008. And after some testing, the whole project was acquired by our present owner. It's the Pfalzwerke Group, which is a public utility company owned by roughly 75% by the local communities in southwestern Palatina. And under their application, the second well has been drilled with the same group of actors, so the drilling company and the engineering company. And then they conducted an intensive test phase to examine the flow rate and temperature of the brine. And as one of the outcomes of this test phase was to drill a further sidetrack in our first well, which is today the re-injection well, to have a better permeability in the brine, in the reservoir, and to allow lower re-injection pressure. The reason why we did so, I will come back to that later. And then the power plant went in operation in November 2012, so almost 10 years from now. So the reservoir was developed from a very small databases. Only two 2D seismic lines were available in those times. But anyway, the geophysics and geologists were able to design a very roughly reservoir model, which is shown here. And we explored several geological sections to get access to the brine. So from the bottom to the top, it has been the top granite, so the basement, the base tertiary, which is the Bunter sandstone in our area, and the limestone. And all of these are connected to our both wells. So we receive our brine as a mixture from 3 different geological sections. And it will be one of the tasks in the future to further explore what are the differences between these different reservoir sections and what is the influence on the lithium inflow. So the technical data of our project with the brine temperature of 165 degrees, we are producing up to 70 liters per second, which is roughly 2.5 million cubic meters of brine per year. And the maximum electric output is about 5 to 5.5 megawatt electricity. And we are able up to produce 35 gigawatt hours electricity per year. Until now, there is no thermal output, but we are discussing several projects. And we have to keep in mind that all these binary power plants have an on-site power demand of about 25% of the produced electricity. And the financial basis is the remuneration under the German Renewable Energy Law, which guarantees 25 euro cents per kilowatt hour gross for a period of 20 years. That's why the whole project is calculated for a period of 20 years. And the overall investment was a little bit more, but 50 years. But to give you an idea about what you have in Chile so far, so the Cerro Pabellón geothermal power plant in northern Chile is 20 times bigger than ours, but it has been designed and produced by the same company, the Ormet Group from Israel and Nevada in the US. In the Rheingraben, we have to focus very much on the mitigation of induced seismicity, which is definitely not a problem in Chile, as I presume. So we have to keep in mind the perceptual range, which is fairly low, I presume, from a Chilean point of view. And to be far away, getting public acceptance and assuring public acceptance, we assure that we are operating our thermal power plant in the response profile level 1. So we have very low induced seismicity with almost unfeelable ground velocity values of 0.2 to maximum 0.5 millimeters per second. So we are very much below the underneath the perceptual range, but this is mandatory in our particular area to ensure the public acceptance. To gain access to the brine, as we have a very deep reservoir, we are operating a so-called line shaft pump. The pump itself, it's a 39-stage circular pump, is installed at 750 meters depth and is driven by a driving shaft or a line shaft, which of course then has a length of 700 meters as well. Looks quite complicated, but once you have got familiar with the whole system and you have explained or detailed all the problems which might occur, then it is a very reliable system. And the lower picture on the left side shows the operation of a pump exchange. This is the 93rd the 39-stage circulation pump, which has been just before installation into the borehole. And we will have a change of our pump next year in summer again, as including as one of our service procedures. So we have to focus on the brine quality in the upper Rhine-Graben. We have a very high gas content in the brine, which is differing from different sites. But in Insheim, for example, we have roughly 1.2 liters of gas per liter brine. And the brine consists more or less of carbon dioxide, a little bit nitrogen and methane. So when operating the brine system, we have to keep in mind this high gas content and therefore have to operate the whole thermal brine system above the degassing pressure, which is in the Insheim side around 19 bars at the brine temperature of 163 degrees, and at the other two sides it's similar, quite similar. So coming to the lithium situation, definitely the upper Rhine-Graben should be one of the most potentially viable lithium deposits in Europe. As already shown by the other authors, the brine content, the lithium content in our brines is above 150 and 200 milligrams per liter. It differs a little bit from the western to the eastern side of the Rhine-Graben. And we believe in Europe that successful lithium extraction out of the geothermal brines could bring an additional value to the existing and the future geothermal projects, especially when looking at the limited public funding for our geothermal project. Then we have to develop further financing instruments to make these projects possible. And as well, it has a domestic importance, as we will be able to partially add some domestic supply for the strategic raw material lithium in Germany. But as the brine is provided by the geothermal plant, the brine is already above the surface, so it's a very environmental friendly production, as we do not have to install additional facilities to get access to this geothermal and lithium-rich brine. So now I will come to a small walkthrough, a virtual walkthrough through our power plant. We will start when we have a look at this bird view at the production well, then walk around to have a look at our C unit where we are producing the energy. We'll have a look at the largest unit, the air-cooled condenser. Then we have a look at the thermal water treatment facility where the BrineMine test unit has been in operation. And then we will have a look back to the overall sites. Therefore, I have just to switch my screen once again. Give me a second, please. So now we will start at the, we need a little bit patience due to a limited internet performance. So there we have a view at the driving motor of our line shaft pump. This is the production well. And this motor is driving a 750 meter long driving shaft, which is continually greased, and operating our 39 circular pump in the depth of the well. So the hot brine is pumped through these isolated tubes, and the returning cooled brine is flowing through the red, non-isolated tubes. And this container is just a service container where we have installed the greasing unit for the line shaft, and as well a water cooling unit for the top bearings of our line shaft pump. So now the hot brine is coming out of this hole and flowing into these heat exchangers. But at first I would like to give an overall view about the organic Rankine circle unit where we are producing our energy. We have here the turbine being driven by the working fluid, which is isopentane, which is mostly common in the worldwide ORC units, not only built by Ormet or even other providers from Italy or Japan, for example. It secures a high efficiency of the whole process. And once you respect some safety reasons, safety regulations, it offers or allows a very safe operation. So the working fluid, the vaporized working fluid expands in the turbine and flowing on the horizontal side to the left side into the large air-cooled condenser where it will be fully condensed, as we need a fully condensed fluid before we can fully vaporize it once again. On the right side, directly connected to our turbine, is the generator where we are producing up to 4 to 5 megawatt of electricity per year. So when we are switching over to this side, so even in Germany, we need some patience. So here we have the large vaporizer where we vaporize the working fluid, and the vaporized working fluid is then led over by this large tube over to the turbine. These vaporizers and the combined heat preheaters on the other side have to be cleaned biannually, as due to the high mineralization of our brine, we will have a lot of precipitation and scaling effects in our vaporizers, and they have to be disposed of these tube and shell heat exchangers by cleaning off with very high pressure at roughly to 1,000 bars every second year, producing residues which then have to be treated and immobilized to allow them to properly dispose them of. So then I would like to give you an impression of our filter hole where the BrineMine tests have been executed. So once again, the hot brine is coming in from the production well, will be filtered with 2 filters. There's simple basket filters with a mesh of roughly 150 microns. And then the brine will be, or we are injecting certain injectors into the brine to avoid scaling effects out of the brine. So the first one is a phosphonic acid to prevent barium sulfide from scaling out of our brine. And the second product is a combined product to prevent all the piping system from corrosion. So it's setting up an anti-corrosion film within our piping system. And then this hot brine and conditioned brine will be injected in our heat exchangers by this tube, and the returning cooled down brine, we're at a temperature of in the average of 65 to 70 degrees Celsius, is returning back into our filter hole, then has to be filtered as well by a double filter group, as we have to prevent the scalings out of the returning fluid, not to clog our reservoir by pumping in these scalings into the reservoir. And in this particular place, the BrineMine unit has been in operation and was connected to the brine circuit via these valves, as you have seen in the video. So this, let's have to keep our time, have a short overview back to the site. So there you can have a look in the wonderful Southern Palatina wine area. So whenever your way leads you to inside, so you're heartily welcomed. And not only we are producing energy and potentially some rare earths in the near future, but as well, we are regularly producing wine from the close by vineyard, which is an excellent dry Riesling. So whenever you have time to stop by, you will have a wonderful bottle of Riesling as a giveaway. So thank you very much for your interest. And if there are any questions, of course, I will be happy to answer them.
Gracias, Jörg. Muy interesante tu presentación.
Well, thank you so much, Jörg. That's a
y
very
las
interesting
presentaciones
presentation.
también las vamos a hacerte llegar.
Making sure that these presentations can be shared later on. Okay, so we have one more presentation from one of the most important actors at the Atacama Salt Flat, which is SQM. Pablo Melipillan, head of the Lithium Innovation, will share his perspective on the perspective of lithium and other valuable metal minings from non-conventional sources in Chile.
Hello, everyone. Denise, are you going to share the presentation?
Yes, we can share the presentation for you. Next slide, please. Thank you.
Yes. Yeah, let's move to the next one, please. Yeah, so this slide is, if you want to invest in SQM, you have to read carefully this statement. So yeah, just move to the next one. Okay, here's the agenda. We're going to review some topics about SQM, who we are. Then we're going to review the lithium and potash mining. Then some figures about sustainability, and at the end, some final remarks. So let's start with some information about the company. So please, the next one. Okay, so SQM had 5 different business units. So as you can see here, we participate in the business of lithium, special nutrition, iodine, potash, and some industrial chemicals. Last year, 2020, we had some revenues around 1 billion, and about 70% of our gross profits came from nutrition and iodine products. So let's move to the next one, please. Okay, so where are all these products coming from? So we have 2 main mineral sources. One is the caliche. Caliche, we have our mines in the northern region of Chile called Iquique. And the other one is brines. And brines, probably as you know, or you know, we obtain brines from Salar de Atacama. In the next slide, we're going to see the products that we obtain from these 2 resources. From caliche, we produce iodine and also sodium nitrates. And from brines, we produce potassium as potassium chloride and also lithium. So at the end of the process in Salar de Atacama, we obtain a highly concentrated lithium brine. And also from our potassium from Salar de Atacama and our nitrate from caliche, at the end, we also obtain another product that is potassium nitrate. If we move to the next slide, we're going to see, okay, a little bit, let's focus on lithium and potassium mining. And let's go in deep in what we do in Atacama Salar. Okay, here, as you can see in the picture, on the left at the bottom, there are some ponds. This is our pond system for making lithium products and also for making potassium products. Okay, how we do it? How it works? We take the brines from wells. So from the Salar de Atacama, we pump brines out. We have different wells surrounding all these solar ponds, and we put this brine in halide ponds. In these halide ponds, what we do is to remove all the sodium chloride that is in the brine, most of the sodium chloride actually, because all the brine that come out from the ponds, from the wells, sorry, it's already saturated in sodium chloride. So what we do after this is to move the brine to the next group of ponds, which call sylvanites. And in these ponds, we get some potassium salts. So these potassium salts for us are a product. So we put in a plant in the Solar Atacama, we have a facility for processing these salts and finally get 95% purity potassium chlorate. Also for these brines at Atacama, we can produce potassium sulfate that we did a couple of years ago. Then after the brine, after we remove or after we precipitate all the potassium chlorate from the brine, we move this to another group of ponds. In this group of ponds, we precipitate all the magnesium chlorate that was remaining in the brine with the goal of then move to another group of ponds in order to obtain a highly concentrated lithium brine. So our goal here is to reach close to 6% lithium as a concentration, weight by weight, in solution. And that is the end of the production process in the Solar Atacama. What we do with this brine, we move in trucks to our chemical plants in Antofagasta. And if we move to the next slide, we can see what we do in Antofagasta is to take the brine, remove some impurities, remove boron mainly, then some calcium, some magnesium that is still remaining in the brine, and at the end, we produce lithium carbonate. And also we have the chance to produce lithium hydroxide. So we take this lithium carbonate, it's a main raw material for the production of lithium hydroxide. So that is what we do with our resource in Solar Atacama. And as you can see, we can obtain different products, potash, lithium, and also, if you want, we can get some magnesium chloride, it's a bisulfite product that can be used for improving the road. So you can use this for removing the dust in the roads. That is a chemical product that is already used in mining companies here in Chile. Okay, so let's move to the next slide and let's see some figures about what is the water consumption for this lithium production, what is the CO2 emission for this all projections that are to come. So in the next slide, we're going to see our water footprint. So this study, these numbers are coming from a LCA, life cycle assessment we conducted last year. And if we say lithium carbonate from brines in a basin of crate to gate, which means including all the water consumption that is used for our suppliers, for the energy we use in the facilities, and also all the water that is used within our production process. If you see the figure, is close to 600 liters per kilogram of product for lithium carbonate. But if you see in some bullets behind the charts in the right, you also can see that we have a figure that is 22 liters per second, sorry, 22 liters per kilogram of product when we use the base gate to gate, which means the water, the fresh water that is really used just in our process in the Solar Atacama. And when we use water in the process, we just need water for transport the brine from one pond to another pond and from the wells to the halide ponds. So just we need water for dilution, and it is a very, very small quantity of fresh water that we need for moving all the brine across the whole pond system. We are doing also a lot of effort for reducing that figure, and today we have reached a significant lower figure than the 22. Okay, so on the next slide we're going to see the carbon footprint. Okay, So here we can see in the right chart the kilogram of CO2 equivalent per kilogram of lithium carbonate equivalent. Okay, so what we can see here is we make a comparison between brines emissions, lithium coming from brines, and lithium coming from spodumene. Okay, so we can see that in both products, lithium carbonate, lithium hydroxide, the brine sources show a less carbon emission compared with lithium coming from spodumene. Okay, so that's it, our carbon footprint, also based in the LCA we prepared in 2020. And let's move to the next one. Next slide, where we can see just a summary. It is a summary of the energy, the total energy consumed by lithium coming from brines versus also lithium coming from spodumene. Okay, so again, here we can see a big difference between lithium carbonate and lithium hydroxide from the both different sources. Okay, so let's move to the next one, please. Here we can see our goals for 2030. We have a very, very strict goals. We want to reduce the state that we are going to reduce our brine extraction and our water consumption by 2030 by 50%. So, and also we want to be at 2030 carbon neutral in lithium and potash. So all our goals are based on our sustainability statement, and it was public information released some months ago. So also you can see here all the investment that we are making for reaching all these goals. And the next slide, we also, it's important to show for us, and important to do this, is to transparent all our brine extraction. So you can see, if you see at the bottom of the right side, as a link, sqmenlinea.com. So if you go to that link, to the website, you can see in real time all the extraction from our production wells. So it is quite useful tools where you can see every little per second that we are pumping out from the Salar de Atacama. And I think it's the last slide in the next one. No, actually, it's not the last one. So we have a big commit or being sustainable in Salar de Atacama. So that's why we're working with different partners to understand very well all the impacts that are involved in the lithium mining, in the potash mining. Also, we have preparing to apply for different standards like IRMA or ISO. And this is because we are highly committed with doing the best job within the Salar de Atacama. And let's move to the final topic of this presentation. This is our final remarks. So in the next slide, we want to remark that we, actually, yeah, that one, yeah. We have as you saw before, we have an extensive portfolio of products. We participate in 5 different businesses. Today, we have a more than 50-year experience at producing nitrates, iodine, also more than 20-year experience making lithium and potash from the Salar de Atacama. So, and finally, we have to remark as well that we are strong goals for 2030, reducing our carbon emission and also reducing our brine extraction and our fresh water use. And I want to just share the last slide where you can see the key slide for this presentation. The left corner up, you can see all our products. Then next to that, you can see our production process in Atacama. And at the bottom, you can see all our consumption for water, fresh water, and for carbons, and our carbon emission. Okay, so thank you so much.
Gracias, Pablo. Gracias por tu presentación.
Well, thank you so much for that presentation. And well, you're not leaving because you're also going to be part of the discussion panel now. So with this, I would like to give the floor to Iris so that we can start with this last panel discussion. Okay, thank you so much, Denise.
We will do that in English. And I am very honored to moderate this conversation with such a high-level participation of you all experts. We can see on the screen. We have Pablo Meridian, Head of Lithium Innovation SQM. Then we have Michael Schmidt joining us from Germany. Michael is a geologist at the German Mineral Resources Agency, DERA, which is based in Berlin and is part of the Federal Institute for Geosciences and Natural Resources at the Ministry for Economic Affairs and Energy. And then we have Nancy Parada. Nancy is an international brine chemistry consultant with more than 40 years of experience in this field. And we are with Carolina Wexler, country manager at Transmark Chile. Transmark Chile is a Chilean partner of the BrineMine project and part of Transmark Renewables, a global company specialized in the global development of renewable geothermal energy. Hello, Carolina. And we have Erwin Platt. Erwin is CEO at Low Carbon Chile. And he's a chemical engineer, from the University of Chile with a PhD in process engineering from the KIT in Germany. And Low Carbon Chile is a company dedicated to promote the use of nanotechnology as eco-catalysts for fuels in developing green hydrogen projects in the energy field. And Erwin is also a green hydrogen ambassador by the Minister of Energy. So hello to all of you. Please switch on your cameras and I will just start with the questions. And I know we're already on time with our panel discussion, and I will switch to Germany for the first question to DERA, to Michael Schmidt. Hi, Michael.
Hi, Iris.
When we are talking about extraction of raw materials, and especially in the scenario of energy transition and the need for those materials to keep the transition going, actually, what about the demand side for extracted material globally and in Germany? Can you just refer to that topic, please?
Yes. Well, first of all, let me extend my thanks to hosting and organizing this wonderful workshop. Well done. I'm very, very impressed by that. Let me use the example of lithium because we're already running behind schedule. When you look into the year 2020, we've had a global demand of about 60,000 metric tons of lithium for all demand areas. And about 73% of that went already into lithium-ion batteries for the transition from ICE to battery electric vehicles. And when you look into all of the announcements globally, and especially in Germany and Europe, on a global scale, we expect about up to 3,000 gigawatt hours of battery capacity, with 700 of that being in Europe and up to 270 gigawatt hours in Germany on the demand side. So the lithium mining side, the supply side, will have to increase within the next 5 to 10 years, 6 to 8-fold, maybe sometimes, or some references talk about 10-fold increase in mine supply of lithium. So we have a supply situation where you have hard rock sources and brine producers. Brine producers predominantly in South America. We have SQM with us today. And then the hard rock side, mainly in Australia. So in terms of future demand, the supply side has to catch up really hard. That's a large monetary investment. And I think we will need every single lithium source that we can catch in order to get this transition excuse me, this transition going in towards EVs.
Thank you, Michael. And how would you describe the potential of a German-Chilean partnership in the development to have this increase of the supply and to match it with the demand side?
Well, I think over the past 2 years, and nobody really expected that the European industry would grow so strong in the future EV market. I think there has been a transition in the mindset of our companies, especially here on the OEM and battery side within Germany, as you can see, and in the media from all of those announcements. I think there's a transition towards a more sustainable lithium sourcing. So transportation footprint, CO2 footprint, water footprint will become very, very important issues. And so I think, if you look into the media, BMW has already signed a takeoff agreement with Livent in Argentina. So I think, yes, it is on the agenda of the industry to look into more sustainable sourcing. And I think that Chile, Argentina, and maybe other countries in South America are going to be on the forefront of this. And, if you look into the global supply side, if you consider that, already the transportation way from South America is only half as long as from Australia via China. So,
thanks, Michael. Pablo, did you like the answer of Michael? Of Michael, that maybe Chile has an advantage on that to other suppliers. And a question for you also for the supply side at SQM. Do you consider the today presented technology as feasible also for implementing them in your company? Because you were showing how you're doing things now and how you're committed to sustainability plans, etc. Do you look beyond the things you have now? Are there future plans to introduce like new technologies?
Yes, we have been working for several years on seeking and appraisal different new technologies for recovering lithium from brines. And yeah, for sure we are always open to analyze this, to study this. And today we are in a point that we want to understand very well the entire impact of these new technologies. It is not just a matter of some particular units that recover lithium. It's also important to understand very well what will happen later. So the downstream process will be very important. So the water recovery in downstream process, the energy consumption in downstream process. So all of this should be put in an economical evaluation and also in environmental evaluation for understanding properly the energy consumption, the CO2 emission, reagent consumption, also water, before to decide to implement this, for instance, in a brine source.
And if we look at the technology more on the geothermal energy solution we have, is it relevant, the geothermal solutions in the mining sector for like energy use, electricity use and heat use in the processes?
So I believe that geothermal, thinking in the opportunities of the geothermal brines and extracting lithium, for instance, yeah, we believe there is an opportunity since new technologies and also some old sorbent materials that have been in the market for more than 20 years. We believe there are opportunities for making some different minerals from geothermal. But as you saw in the previous presentation, also it is important to understand the potential production from these geothermal sources. So we saw that the lithium content, it's between, I don't know, 200 ppms, more or less. So probably if you want to produce 50,000 tons per year from these resources, it's not possible, won't be possible. But if you want to produce 5,000 and 10,000 tons per year, probably will be an opportunity.
Okay, thank you, Pablo. And I will connect to this question for Carolina. Carolina, the technologies presented today, along with other innovation in this field, how could they actually improve the economics of the overall geothermal energy applications? Because we also had a question in the chat, which is pointing out that we only have one geothermal installation going here in Chile, but we have a huge potential. So how could the economics maybe improve when we give them another use, like the extraction of materials?
Well, thank you. In Transmar Chile, we have been exploring different areas all around Chile for the last 10 years. And we have faced many different challenges to get into a development stage. Some of these challenges sometimes become obstacles for the geothermal development in Chile. And of course, the main issue is the economic and financial issue. And I think, of course, for every project. Unfortunately, in Chile, we don't recognize all the geothermal attributes for electricity generation. And currently, the geothermal electricity in Chile is still pretty much unknown for the country. The geothermal energy has an enormous cascade utilization of the residual heat, like for greenhouses, fish farming, drying wood, heating houses, and among others, utilization. However, none of these improves substantially the financial model of the project. And I think the main reason of this is because the geothermal resources recognize, at least the recognized one in Chile, are mainly located in the Andes chain, which at the end implies that the resources are far away from the grid lines. In case of the geothermal brine for lithium or other valuable mineral extraction, definitely can be an interesting innovation to improve the economic of the project. However, I think the most interesting issue of this BrineMine project, in particular this innovation, is to study the possibility to generate potable water for the nearby project communities. I think that is the valuable issue in the BrineMine. And for mineral extractors, I think like SQM can be a very interesting mining project.
So you mentioned the possibility of extracting fresh water. Maybe back to Germany once again. Michael, the fresh water and the water usage, etc., is that also something, you mentioned it like the water footprint, the carbon footprint of lithium. So if we can extract fresh water with the technology, so this would also improve the water footprint of Chilean lithium, right?
In this context, yes, of course. But those geothermal sources, and that was something that I wanted to say before, is that it really depends on the area where you are or the country in terms of, is it a method that could be of potential supply. So as we heard in one of the previous talks, that geothermal induced seismicity could be a problem. Yes, this could be one of the topics here in Europe, here in Germany, not so much in Chile, of course. So, and on the other side, the production of potable water could be a very good a side effect of one of those projects in Chile or in Argentina, not so much in Germany. So really dependent on where you are globally, this technology has its own or is more suitable than other technologies. But for Chile, that could be of potential. But as we just heard from SQM, geothermal lithium will not be the new source that will be in a large competition to the traditional sources that we have already. It could be a additional source, and I think we will need additional sources, but not to the quantitative extents that we would need on the supply side. So we will still need the traditional pathways of lithium production, but geothermal could be a good sidekick, if you will.
Okay, thank you, Michael. And I have a question for Erwin. Erwin is active in so many fields, and so I want to throw the combination question to you, Erwin. Like, we have energy generation, and then we have the raw material extraction and the energy storage as the use of the material that you can actually extract. Do you think that there's a need of like having an underground thermal water portfolio?
Aris, first of all, thank you for the invitation also from Professor Kohl to be here. I'm very happy to be in this, involved in one or other way with the investigation done in KIT, where I spent a number of years. So having said that, I think I have to center the discussion. We are talking about energy, and we confuse energy with electricity. Electricity is only 22% of all the energy we need. And in all this geothermal, we're going into electricity. I don't know why is that so nice, okay? And if you just hear to the figures that we have heard from Jörg Ude, this project they are doing there has, maybe you didn't catch it, but it has 250 euros per megawatt hour, which is absolutely crazy. The same with the price of the electricity we have in the Cerro Tronador, which is 95. It's ridiculously high. So if we want to have renewables, let's look at the whole picture. And if in Chile we have more than 2 terawatt of renewables, the potential of geothermal is not 1% of all our potential. So the question is about the price. How much do I pay per the megawatt hour? Do I pay now 95, or do I pay 40, or only 10 with photovoltaic? Just having said that. So the potential for me is very little that we have, but okay. What we are forgetting is all the thermal potential. And that's why we have to see the geothermal of low enthalpy, just to heat houses and so on. But we are, for whatever reason, we are concentrating in electricity. And we have better means to have electricity. So coming back to your question, do we have to make the mapping? It's a lot of money. I don't know if we will have the money for doing that, for saying, well, the potential is not 1%, it's 2%, it's 5%, whatever. If we do have renewables at a lower price, that will be the winning game. Now, two things that you are saying. One thing is energy, and we always have had to store electricity because you cannot store electricity in the wires. So how do we store the energy? In a pile of coal or petroleum, whatever. Now, with renewables, it's different because we have to store the electricity after we generate that. And so that we need storage. And just to make it clear, batteries with lithium or whatsoever, it's only 5% of the electricity stored in the world. 91% is pumped storage, so it's gravity. So there are a lot of solutions, and do not concentrate on that. And what we are saying is using hydrogen, but that is only a way of store electricity, nothing else. It's not something new. It's one way how I can get my renewable electricity from here to Germany, for instance, only in a ship, not by cables. So if we will invest in having mapping of all these resources, I don't know. But I love this BrineMine project because I think that's a lifesaver of the geothermal one. Because there is so much money, as we saw, in the resources you can mine there, that all the electricity is something that you get, but the real potential is in mine brine. The same look at the countries that have done a lot with geothermal, like Iceland. Well, you have tourism, you have aquaculture, a lot of things, a lot more holistic than only concentrate on electricity. That's why I want to warn to concentrate on electricity, which is going nowhere, but the heat, we can use it a lot. So geothermal, but with low enthalpy will be one very, very nice thing to have. Thank you.
Perfect, thank you. And do you think, because we had a very interesting presentation from Ruben also about the legal framework, do you think for the BrineMine, the whole legal framework is okay? Is it here? Is it already done? Or is there something to improve?
Yes, and we are improving that. Ruben told it very well. We do have, since 2000, we have this law, 19657 for geothermal, but always thinking on electricity. I don't know why. Now, since 2 years ago, there is a new changing of this law in the parliament. It passed in 1 year, it passed the lower chamber, and now it's in the upper chamber, also a year lying around, and that will split the use of the geothermal energy, low enthalpy, so up to 95 degrees, to heat my house, to heat my buildings, you see, or to cool them. And this will take, I don't know, 1 year or so, but it's because the first law is not good. And we can see that it has gone nowhere, because if I want to heat my house, if I had to pay a concession to bore, I don't know, a hole, it will go nowhere. So it's very good. There is in the parliament right now a change in that law. After 10 years, we saw that it's going nowhere. Because in the first law, geothermal, you can make use of the water, and that collides with the use of water or other uses. And that is a social problem. People think that you will get their water. No, the water in geothermal is 3,000 meters down, has nothing to do with the water we drink or we use for agriculture. So there are two different things. So it's very important to concentrate on where geothermal has some advantages. Norway, we do have the disadvantages. Okay.
Mm-hmm. Thank you, Erwin. You came back to the water issue and the use of the water, etc. And when this comes into my mind, I'm thinking like of extracting something and not giving it back to nature. So talking about closing circles and circular economy, etc. And I would want to give Nancy the chance to talk about it, and I'll switch shortly in Spanish. Nancy, como experta química, la tecnología que
As a chemical expert, the technology presented, how this could be a solution that will approach mining so as to close the circles. So, will we ever reach this circular economy? Could you show us this concept?
Yes, thank you, Iris. Thank you, Denise, for giving me the opportunity to participate in this panel. Well, I think that geothermal energy is circular mining already, because when doing the drilling in order to extract the liquid and also the gas, you have to re-inject it. And in that simple process, you take full advantage. And since there's no invasion of the surface aquifers, you do not impact the environment, which is what people are mostly concerned with, the people that live in those areas, or at least in lower altitudes, because these deposits tend to be above 3,500 meters above sea level. So the impact in terms of the people who live in the sector is lower. Now, I want to follow what Pablo was saying before. The amounts of lithium in our brines, in our geothermal brines, have always been considered as sub-economic resources, given the concentrations. This was a while ago. But now, given the high levels of demand, it comes, or they come as an alternative, but by using other recovery methods, which are direct extraction methods of lithium, and then for that, there are technologies that have already been developed, and they use the specific extraction of lithium based on a polymer developed by Dow, plus alumina. So now, given if the flow of elements is actually quite broad, then there are also special or specific resins for the extraction of those minerals. So the problem is the levels of concentration. In the case of brines, it is clear that it's not water. These are minerals because they have a 28% minerals and 72% of water. So in the case of geothermal brines, the amount of total dissolved solids that Valentin talked about is less than 1%. And the largest quantity is silica, which is the big problem. And fortunately, regulating pH, it is possible to remove it from the system and to re-inject it or to provide potable water. It'll depend on the variability of the other existing elements. So I think that by definition, the geothermal process of energy recovery and recovery of other possible elements or providing water is in itself intrinsically the circular economy concept. That is my point of view. Now, also, I want to build on what Pablo said. We cannot think about a large lithium production capacity, given that there are small flows and given that the concentrations are low. And it all depends on the geological environment or surroundings in the area. That's what I believe.
Super, muchas gracias, Nancy.
Well, thank you so much, Nancy.
Thank you very much for your opinions, for sharing your expertise and your knowledge with us. I saw that Denise just appeared on my screen, so I think that's the sign, the signal for me to stop the conversation. And just to thank you to all of you for being here and for sharing your knowledge with us. Back to Denise.
Gracias, Iris. Y también gracias a nuestros panelistas.
Thank you, Iris. I would like to thank the members of the panel, for the audience, and for staying with us until now. So to close the event, I would like to give the floor once more to Thomas Cole for him to deliver then the closing words.
Gracias por la organización y gracias por su...
No, thank you. Thank you for those presentations. Thank you for all your contributions, for the dialogue in this BrineMine webinar.
Some interesting aspects in my conclusion. I just was preparing a slide, but I didn't finish it up. But you will get it in the final documents. I think we have got a number of good ideas and results, and especially just have to look on the other screen here, especially BrineMine shows that there's a need for new technology development that takes place in the term of the energy transition. So we cannot continue with the same technology. We need to develop new tools, and I think BrineMine is one of these aspects that is exactly in the way to foster and to support the energy transition in future. It is a way to go into circular economics. It is definitely not only limited to lithium extraction that we have been discussing here, but we have many other applications that are possible in this BrineMine technology. It is leading to a new process engineering to reduce the use of fresh water, and also this is helping a lot into legal conflicts that arise right now in the mining, in the geothermal, and all these underground technologies So we might also give something to the local population, to the indigenous population, to support them and to show them that the underground technology is not only destroying their environment, but it's also supporting their environment. It might have a lot of economic benefits for geothermal. There are perspectives on geothermal, so to improve the economics. We have also discussing the point of using more direct use in geothermal. But the application in mining industry might continue further on. So we could think, is a technology transferable to mining? It can be applied to mine tailings, or can it be applied to leaching technology? So I hope very much, and I would like to conclude with this, that it is a collaborative effort. We can support the German-Chilean collaboration on this issue further on. And so it is a resource. We can extract possibly resources for a high-tech market, with Germany being a long-term market or export market in this concern. So there might be also some long-term perspectives that we could try to develop. Anyhow, I would like to thank you all very much for this workshop and for the participation, and Denise and Kamchal, very much for your organization, and to the leading through the project. Also, we got a little bit late today, but I hope you're still online here. Thank you very much.
Perfecto. Muchas gracias, Tomás. Gracias al consorcio de BrineMine por presentarnos este interesante enfoque.
No, thank you, Tom. I want to thank BrineMine Consortium, and we wish you the best of success in the next stage. And I want to invite all the audience. The members of the panel from Germany have already shared their contacts throughout the chat, and you can also get in touch with them through us, through Kamchal. So we hope that you have a very pleasant afternoon, and we will see you in the next opportunity. Thank you so much.